Neptune moves around the Sun at an average distance of about 30 astronomical units, which means it is roughly 30 times farther from the Sun than Earth. At that range, the sunlight that reaches the planet becomes extremely weak. The radiance measured near Neptune is about 1/900th of what reaches Earth. This low-light environment defines many of the planet's observational and physical characteristics. A full Neptunian orbit lasts 164.8 Earth years, which can be read simply as about 165 Earth-year cycles. Any attempt to track long-term patterns on Neptune must acknowledge that its seasonal changes unfold on timescales far beyond a human lifespan. Even a century of monitoring would barely cover a fraction of a single Neptunian year. Neptune carries a mass of approximately 1 nonillion kilograms, and the value is about 17 times Earth mass. Pressures inside Neptune rise to levels between 1 million bar and 10 million bar. These figures correspond to millions of times Earth's sea level atmospheric pressure. The temperature at the core may exceed 7,000 Kelvin, while the highest cloud layers sit near 55 Kelvin. Neptune emits roughly 2.61 times more energy than it absorbs from the Sun. Despite receiving minimal sunlight, the planet behaves as an active thermal system with continuous internal output. The visible appearance of Neptune is shaped strongly by methane in the upper atmosphere. Methane absorbs red wavelengths with significant strength, causing the emitted and reflected light to shift in favor of shorter wavelengths. This effect makes Neptune appear around 10 times bluer than Uranus under similar lighting conditions. Observations confirm flows reaching 2,100 kilometers per hour, which is about 10 times faster than the strongest storms measured on Earth. These motions vary with depth and latitude, forming alternating bands and large rotating systems. One landmark example was documented during the Voyager 2 flyby in 1989, a vast vortex known as the Great Dark Spot. The energy involved in this downward motion has been estimated at roughly 10,000 times the energy released by rain processes on Earth. Below the visible atmosphere lies a mantle composed of supercritical water, ammonia, and methane. This layer extends to a depth of roughly 10,000 kilometers. The conditions remove the typical boundary between liquid and gas, producing a continuous fluid zone capable of significant convection. Instead of being nearly centered and aligned with the axis of rotation, the Neptunian magnetic dipole is tilted by 47 degrees, and it displaced from the planet geometric center by roughly 0.55 planetary radii. When compared with Earth's magnetic offset and tilt, this configuration is about 10 times more extreme. The unusual geometry suggests that the magnetic field is generated not in a metallic core, but within the convective supercritical region of the mantle. The Neptunian system includes the large captured moon Triton, whose retrograde orbit confirms that it did not form along with Neptune. Triton is spiraling inward at a rate of about 10 centimeters per year. Models indicate that in roughly 1 billion years, it will move past the distance at which its structure can remain stable. Triton also exhibits active cryogenic processes. Its thin nitrogen atmosphere, held at a pressure close to 1/1000th of a bar, allows geysers to erupt with unusual reach. Some of these plumes can climb as high as 8 kilometers. For comparison, Earth's tallest geysers rise only a few tens of meters, meaning Triton jets reach about 1,000 times the height of their terrestrial counterparts. These measurements build a coherent picture of Neptune as a world shaped by broad physical extremes. Its 164.8 Earth-year period dictates that seasonal and climatic cycles evolve at a scale unfamiliar to life on Earth. Its mass drives gravity much stronger than terrestrial norms. Winds exceeding 2,000 kilometers per hour, the planet emits more than double the energy it receives, signaling internal heat sources at work. Methane absorption sculpts its blue color. Storm systems can cover areas measured in trillions of square meters. The supercritical mantle reaches depths of about 10,000 kilometers. Neptune demonstrates how physical laws operate under extreme scale factors. Distance, mass, pressure, temperature, magnetic geometry, and atmospheric motion all push beyond familiar Earth-based ranges. It makes the planet a prime example of large-scale planetary physics in action.